morning, folks. Let's see.
Good morning.
Morning, good morning. Let's see. We have another amazing turnout. We've got a good number of folks here. Let's see. 1, 2, 3, 4, 5. We got 50 people here this morning. That is amazing. Okie dokie. So, y'all can see the PowerPoint here, right?
Yes.
Okay, perfect. So last time I think we finished section 1.3 with calculation about parts per million or parts per billion of something, an acid or something like that. Is that? Do you guys recall that?
Yes, we finished. Not this one.
We didn't do this one. So how about let's see, that's the one I'm just thinking about doing. With these to create a solution by dilution. Did we do these?
Nope, we haven't done these either.
Haven't done them. Oh my gosh. Okay. I was getting ready to jump ahead. So let's do a couple of these guys. There we go. It's probably this is probably where we left off. It was like maybe this guy here.
Yes, parts per million and parts per billion. That's where I
think. Okay. So did we do this one?
We haven't done this one, but I think we talked, I guess.
Okay, all right. We'll go ahead and do this one then. Thank you, Alvin. Excellent. I noticed that you changed your profile picture.
Oops. I don't know, because of some reason I had two Zoom or something like that, which I didn't realize. So one of my, like meeting while
Interesting.
Yeah.
Okay. All right. Well, let's see here. Okay. So parts per billion, parts per million, and stuff like that. Let's go over them real quick. The idea here is that ppm, ppb, etc. They're just mass over mass, basically. This is a stupid example. So yeah, it's mass over mass, mass of substance over mass of sample, right? So when you use parts per million and parts per billion, 99.9% of the time, you're talking about 3 sig figs, maybe 4, and that's really it. I mean, if there's something else going on, if you're working at a super high accuracy place, then you have to be careful. But those settings are very well identified. So massive substance over massive sample becomes massive substance over mass of solvent or solution, because they are the same to within a few parts per billion. So ppm and ppb, you can substitute the milliliters of solvent or the liters of solvent. You know? And so a part per million is a microgram per mil or a milligram per liter. And a part per billion is a nanogram per mil or a microgram per liter.
And
So,
Professor Terrell, there is a typo there. It should be billion, but there is million.
Yes, thank you very much. Ah, thank you very much.
Yes, sir.
This M should be a B. It's italic. No, it's italic. So, words per billion. Yeah. So, so you can think about it as, you know, a milligram is like a little speck, and you can normally see a milligram like of salt, or it might be a grain of salt or something like that. If you toss that grain of salt into an entire liter of solvent, then you've got 1 part per million. Part per billion is 1,000 times less than that. So ppbs are very low concentrations. ppm are low, but sort of like accessible to the human. Right? So as a chemist, if you see a part per billion of something, it could be a pesticide or whatever, you've got to think, okay, is that dangerous? You know? You got to think because chemists and scientists and instrumentation and whatnot, we're able to measure stuff that is really, really like vanishingly small concentrations. So just kind of be aware of that, like as you go forward and you represent yourself as a chemist, that if you have a method that can resolve a few parts per billion of something, it doesn't mean that there's any problem necessarily. Right? And one that you have used or will probably be using is GC mass spec. And GCMS can often detect or quantify a few parts per billion. So anyway, blah, blah. That's enough of that. Let's move on. So for example, converting PPB into molarity. Well, you need, if you have a hydrocarbon, for example, C29H60, right? Then, and someone says, oh, that's 34 parts per billion, right? Then you might want to find the molarity, right? Of this guy, you know? And then you want to use also a prefix like nano or micro or whatever. So let's see how they do this. So 34 parts per billion is 34 nanograms per gram, right? Nano is 10 to the minus 9, and a gram is 1, right? So nanograms per gram. And there's a little disjoint here when you go from grams to milliliters, because 1 gram is 1 milliliter, right? Liters, it's kind of unfortunate that unit got used because the kilogram is really the basis mass in SI units. So anyway, so and a kilogram and a liter are the same, you know. So nanograms per gram or nanograms per mils are the same. And so to find the molarity, first we calculate how many grams are contained in a liter, right? So 34 nanograms per mil. And they do these compound things, like they're going to change 4 units here, right? 1,000 mils per liter, right? So this liter is in the denominator, so it comes down here. And this microgram is in the denominator, so it goes for the numerator. So nanograms per mil becomes micrograms per liter. That's pretty simple, right? That sets us up to do molarity calculation there, right? So C29860 is 29 times 12, 60 times 1 is 409, roughly, right? And then 34 grams, 34 times 7 minus 6, right? This is micrograms, 34 micrograms over 408 grams per mole is 8.3 times 20 minus 8 molar, right? So it's 6 and then 7, 8, something like that. So that looks correct, right? So now, in order to convert this into a proper prefix, you go 10 minus 8 is close to 9, right? So you can divide this by 10 minus 9, yeah, and get nanomolar. So 83 nanomolar. Which, by the way, is really freaking low. Hard per billion, there you go. So let's do this one. How many parts per billion of this wax are in 23 micromoles? Are in 23 micromolars?
Professor Terrell, sorry to interrupt,
Yes.
but it seems like we have done this. I just checked my note. We did this one and found 9.402 milligram as an answer.
Well, there you go. That was my answer too.
All right. So I'm really sorry.
No, that's okay. That's all right. That's all
My
right.
last note that I have, I don't know about other, friends, is till foil 53 of notes, which is concentrated nitric acid. That's the problem we did. C1V1 equals C2V2.
Oh, so we got through this stuff. Okay. Well, okay. So I'm not going to do this one then. That's good information. Thank you. And sorry, I just forgot where I left off. I'll make a note of it. But we got through nitric acid, right? That's right. So yeah, so nitric acid, that's going to be this one. Well, so we did copper sulfate then?
Yes, molar mass of copper sulfate.
Okay. Copper sulfate, nitric acid. So, okay. So this is just dilution, basically. So, so they talk about how to prepare. This is actually a really important skill, so I will take a little bit of time with it. But because always in the lab, you're always confronted with concentrated acids. So they give you 12.1 molar HCl and concentrated nitric, it's like 16 molar, and concentrated sulfuric, it's like 18 molar, right? And all of these acids are concentrated to the maximum that you can concentrate. You just can't make more concentrated acids. Because if you do, they decompose or they outgas or whatever, right? So you always are having to dilute these, right? And so the first way to do this is M1 V1 equals M2. Right? And let's see here. Get this off to. So if we want to do M1 V1, what does this mean basically? Well, M is a concentration in moles per liter, and V is a volume preferably in liters, although you'll see where we can budget if we use milliliters on both sides. And this is moles per liter times liters. Right? Um, so, what does this mean? This means moles equals moles. And what this means is that if you take a certain amount of like solute, and you can imagine the solute for the moment being in a pipette. Right? You've got this amount of stuff in here. And there is, there's, say, water and HNO3 in here, right? And the number of moles of HNO3 is equal to the volume, call that V1, times the concentration, C1. Right? Or concentration M1, right? And so this is equal to the number of moles of solute in the pipette. Then if what you do next is you put that into a larger vol flask, right? And then you dilute it to the mark with water. So you pipette in the concentrated solution, and you add water. And typically what you do is you add it up to about here, and then you swirl, and then you add water to the mark. And I don't have to get too much in the weeds here, but if you're going dropwise, you can use a pipette, use a Pasteur pipette. Okay, it's a little, basically use a dropper, and then you invert 10,000 times, right? And then so this is V2 here, right? This is V2, and the new concentration is C2 or M2, right? And so that all this means is that all of the moles here transferred down here, right? So now you have a new volume with the same number of moles. So you can solve for E2 or M2 or V1 or M1 using this, as long as you're, just talking about transferring a volume. So for the case of a concentrated acid, right, what we have is, let's see, we've got 12 moles times X moles, right? This is how much of this concentration to make 0.1 moles of 1 liter of 0.1 mole, right? So here we're using molar and milliliters, right? And molar times milliliters makes millimoles. Right? So I'll just write that down. So concentration in moles per liter times volume in milliliters, right, is actually identical to number of millimoles. And I don't know how to justify that. I just happen to know that it's true, right? And so that's what's happening here is we're saying that the millimoles before dilution is equal to the millimoles after dilution. So to make, so you do this calculation, right, and you get that X here is a small value. It's about 9, or it's about 8.26 mils, right? So you'll have to, in order to do this, you'll have to take a concentrated acid and take this small volume with a auto pipette. So not actually that common thing to do. A lot of times you'll let this concentration float. You say, well, I can use 10 mils here. Use a glass pipette and take up 10 mils, right? Then you'll recalculate the molarity. But in this case, let's assume that we can pipette 8.26 mils here, right? And then you put that into a liter flask, add about 900 mils of water, swish, 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 add enough water to top it off, and then dilute to 1 liter, right? And then this concentration should be close to 12.1. It will not be exact, right? So because the reagent here, the concentrated acid, is not exactly at 12.1. The reason is that every time you open an HCl bottle, a concentrated HCl bottle, a little bit of HCl gas escapes. And then when you recap it, a little more will evaporate, you open it, a little more escapes. So the concentration will be coming down slowly. So that's just sort of a practical point. So why don't I have you guys work on this for just a couple minutes? And I actually have to take a quick break, and I will Sorry, everybody. I'm back. So 15.8 molar nitric, right, times times some volume will be equal to 0.25 liters at 3 molar. .00 molar, right? So V1 here will simply be 0.25 O liters times 3.00 moles per liter divided by 15.8 moles per liter, right? And that will be equal to 47.5. Yes. All right. Oops. I should probably show you what I'm doing here. There we go. So sorry. It was a good thing I went to the bathroom. Trust me. So, so, let's see. That's about half of the lecture. So let's see. Let's also talk a little bit about density of these guys. So if you, typically what happens is, and this is actually a stupid one, you don't have to, because they say it's more complicated. It's exactly the same idea here. That you take, well, this is more complicated, not because ammonia is in equilibrium with ammonium hydroxide. Let me see this. Right? Ammonia and water makes ammonium hydroxide. This is basically just, you know, something that happens to ammonia when you dissolve it in water. Now, ammonia is the smell of window cleaner. Almost all, I mean, there's a few with acetic acid now, but most window cleaner has ammonia in it, right? It's kind of like, that's kind of like that, I don't know, bitter or whatever smell. And it's slippery if it gets on your skin because it does a little bit of protein hydrolysis and it starts to dissolve the skin. And so that's what makes it slippery. So, but ammonium hydroxide and con-nitrate, con-HCl, con-sulfuric, con-HF, all these things that come as percents by weight, right? So it's this many grams of ammonia, right, per 100 mils, right? And then, so grams per 100 grams, rather, 28 grams of ammonia per 100 grams of solvent, right? And then they tell you this to convert grams to mLs, right? Grams to mils. So they don't actually tell you the molar concentration. They just tell you the percent and the density. And then they say, okay, now you're going to make a molar concentration. So you gotta sort of translate it. So the way that that's done is here they've done it all in one step here. So you take this is the density, and then this is 28%, right? 0.280 grams of ammonia per gram of solution, right? And then grams of ammonia down here cancels with grams of ammonia up here, grams of solution there. You've got liters in the denominator and moles in the denominator in the denominator. So this is moles per liter, right? I can't edit that right now. Okay. And capital M moles per liter, right? It'd be moles of NH3. Okay. So does that make sense to everybody? The crowd gives a huge yes. Yes, Dr. T, please move on. Does that not make sense to anybody? No, Dr. T, don't move on. Well, I'm going to move on because there's no answer right now. So let's see here. So this is just that answer, I guess. Here. And then we can do a 70% nitrate problem here. So for example, we can take what we want to compute, right? First, we'll put down what we want. Is the number of milliliters, milliliters, this is a volume, of 15.8 molar, that's moles per liter, concentrated nitric acid to make 250 moles of 3.0 molar. Right? So, you know what? That one's, is that even the right question? Yeah, I think I got the right question. Yeah, I got the right question here. This is actually, this is the right question. So the question I want is, the number of mils of HNO3 the molarity, no, sorry, the molarity of HNO3 given a couple of facts, that it's 70.4% by weight, and the density is 1.41 grams per ml. Right? And then the formula weight of HNO3, that we've already told me here, is 63.012 grams per mole. Okay. This is all the information we need to calculate the molarity. So first we'll start out with the concentration in weight. It's going to be 70.4 grams of HNO3 divided by 100 grams of solution. Now this is this viscous syrupy solution, right? Now we want to go from grams of solution to volume. Right? multiply this by 1.41 grams of solution for 1.0 milliliters of solution. Right? It's actually just exactly 1 mole. And then we can multiply this guy by 1 mole of HNO3 for 63.012 grams of HNO3. This is to convert between grams and moles. Right? We're going to multiply that by 1,000 milliliters per liter. This comes out to 15.79 moles of HNO3 per liter. So I'm sorry about I got under the wrong page there. I don't know how it happened, but that's how you calculate the number of moles, or the molarity of a concentrated acid. Is you start with the percent concentration. This is the percent cons. And you multiply by the density. And you basically divide by the formula rate and multiply by 1,000 mLs per liter. And there you have it, 15.79 moles of HNO3 per liter. So, when you guys are finished copying this down, we're going to move on to some calculations related to the gravimetric analysis. Right? So gravimetric analysis is gravimetric and volumetric, they call it. Volumetric analysis is generally titration. So a gravimetric analysis is where you react something and you're trying to take some part of that solution and make it into a solid, ideally a pure solid that you can then weigh. And then the weight of it will tell you the concentration. And then the volumetric part is you react it with some standard acid or base or some nitrate, right? And then the amount of that standard will tell you the concentration of the thing that you're reacting with. So, let's move forward here. Oops, yeah, this is for gravimetric analysis, right? So that's what I just said. That the gravimetric and the titrometric are actually quite precise and accurate, right? So you can repeat them well, and they give good answers, right? Because basically a gravimetric analysis is you can use standard weights and calibrate to them, and they just come out just about perfectly. And as long as you have a pure standard, then volumetric can come out really well too. They're not quite as good as balances, but a long, skinny burette can be pretty accurate. So, so to take an example of this, you could determine the iron content of a vitamin tablet by basically first you dissolve it and you filter it, and then you react the iron with peroxide to make it into iron 3. This is just a quantitative reaction. This goes to completion, right? There's no equilibrium errors here. And because for one thing, you use an excess of H2O2, right? And that will create quantitatively iron 3 from iron 2. To maybe, 99.99999%, right? And then you take that iron 3 and you react it with hydroxide iron. In this case, you can use ammonium hydroxide. And then that will take up a little bit of water and it will make this gel, this gelatinous iron oxide hydroxide. And this is iron 3 because you've got a -2 ion and a -1 ion. -2 ion is the oxygen, and the -1 ion is the hydroxide. And then you can take this gel and heat it to bloody hot, 900 degrees centigrade, which is like 1,500 degrees Fahrenheit. And that will leave you with a solid. This will leave you basically with rust, iron oxide here. And then you basically just weigh the iron oxide. And so, so one of the first questions that you have when you do a gravimetric analysis is you have to ask yourself, how much product do I need to weigh in the end to get the accuracy and the precision that I want, right? And a typical balance will go to the 0.1 milligram. So when we go basically, this is gram, and then we go 1, 2, 3. That's milligrams. So 0.25 is 250 milligrams. And then most balances now will go to the 10th milligram. So if you get 250.x milligrams, that will give you plenty of precision. So you can say, well, how much iron, how many tablets, right, do we need to get this much product? So the way to do that is you look back at the stoichiometrics. Well, here, there's no change in mass here, in the oxidation. But here we've got iron Fe2O3, right? We've got Fe plus 3. Right? And if each tablet provides 15 milligrams of iron, then how do we get 0.25 grams of this stuff here at the end, right? So the way that you do that is first you can say, well, let's calculate the number of moles of iron oxide that we need. And there's a little calculation here that I'm sure you can do. 55 over 1. That's, again, just the 2 sig figs. That's 1.6 millimoles, right? 1.6 millimoles. And if each mole of iron oxide has 2 moles of iron, then a quarter gram of iron oxide then what you can use as well, so this is starting at 0.25 grams, right? That's 1.6 millimoles. You say, well, there's 2 moles of iron for one, that's 3.2 moles of iron. Right? 1.6, 16 to 32, right? And then 32 millimoles, we convert that to grams using the formula rate of iron. And that gives us 0.18 grams of iron. Now each tablet contains 15 rings. So what we do is we take 0.18 grams here, and we divide that by 15 milligrams per tablet, 0.015 grams per tablet. That comes out to 12 tablets. So 2 sig figs here is all we do. This might be exact, but it doesn't really matter. If you got like 11.5 or 12.5 or whatever, you just say 12. Because all you're doing is shooting together, right? So here we can do a calculation. If each tablet weighs 20 mgs, how many tablets do you need a half gram? Right? Look at the stoichiometry again. Then we can, oh, I see. Okay, so we can do this one, but I'll leave that as an exercise for you. So 1 mass of 3% peroxide is required to provide 50% excess, right? Of peroxide. So this is H2O2. Oh, shit. So 50% excess of H2O2. Now, if you got 3%, how much do you need to put it to get 50% excess? So reaction 1.7. So this is back to the 12 tablet idea. And you can multiply that by the expected concentration. That gives us the total amount of iron, right? And it gives the total number of, say, millimoles of iron. And the millimoles of iron, for every millimole of iron, you need 2 millimoles. Right, so for every millimole of iron, you need half millimoles of peroxide. So this is 1 of these, 2 of these, right? And then, so you just multiply this moles of iron by 1 mole of peroxide divided by 2 moles of iron. That gives you 1.6 millimoles of peroxide. And at 50% excess, which means you want to use 1.5 times that. So 1.5 times 1.6 is 2.4 times 10 minus third moles of peroxide. So this is really the sweet spot here. This is, we've solved the problem here, but we only have it in terms of moles of peroxide. So what we need to do is say, no, that number of moles is how much peroxide. Well, we multiply by 34 grams per mole here, and that gives us the number of grams of peroxide that we need. Right? Still not quite there, because peroxide is 3% solution. Right? So the mass of solution is 0.082 divided by 0.03 grams per gram. This is 3%, 0.03 grams per gram of solution, right? And so the gram of solution is in the denominator here, so it pops up to the numerator here. And this is the mass of H2O2 solution, 2.7 grams, or roughly 2.7 mLs, right? So this is going to be 1 gram is equal to 1 ml. Right? You know, it's approximately equal to that, you know? And that's all we need to know here, because this is just computing how much excess. And we'll just, this is an approximation here. This is approximation, you know, and 50% excess, right? This is another approximation. So basically, this is how you do these problems. And we will get to the, you know, I'll show you, I'll actually post the solutions to this guy on the web. And then we're probably going to move on to the next chapter on Thursday. You know, maybe I'll post the solutions here, and you guys can peek at them to do the homework on this guy. But that will be for Thursday. And for right now, are there any questions? Anything I've forgotten or done wrong? Anybody still struggling with sapling? Trying to get the homework? Anything I can help anybody with at this point? Alrighty, so thank you so much, and I look forward to seeing you all again Thursday. Try to keep up with the homework, and I will post this stuff as I'll post this all later today. Okay. See y'all on Thursday. Good luck with the homework.
Thank you. Bye.
Have a good one, Dr. Cherry.
Thanks. Bye bye.
Thank you.